Okay, perfect. So welcome everybody to the webinar of today. The speaker of today is Jean-François Berret, and he will talk about the importance, the title of his presentation is on the importance of lung fluid rheology for medical applications and toxicology. So as usual, I introduce the speaker and very briefly, and then I leave him the floor. So Dr. Jean-François Berret is an alumnus of the École Nationale Supérieure ENS ULM in Paris with a specialization in physics. He joined the Centre National de la Recherche Scientifique in 1983 at the age of 24. He got his PhD in solid-state physics at the University of Montpellier in 1988 and worked as a postdoc at Mainz University in Germany until 1990. He then moved back to France to work on soft condensed matter and reophysics at the University of Montpellier. He then became CNRS research director in 1999 and was promoted to CNRS research director first class in 2011. He worked 4 years in the United States from 2000 to 2004. For the Rhodia company. His current research focuses on the development of soft matter nanotechnology, including new functional structures, devices and systems with stimuli reactive features at the nano and micro scales. Its objectives are the applications of emerging nanotechnologies in medicine, biology, and the environment. Applications include in vivo imaging and therapy tools, microfluidics and microrheology, and the study of living system-machine interfaces. So it's with great pleasure that I introduced Jean-François Berret. So Jean-François, I stop sharing my screen and you can start sharing yours.
That's it?
Yeah, we see your screen. Perfect.
So, should I start?
Yeah, please go ahead.
Okay. So thank you very much, Francesco, for this introduction, and thank you here to be here, a little bit in the cold. I realized coming here that my topic of research is a bit away from what you are doing here. So I hope you will be interested. I will try to make it interesting. But I hope you will also see the relationship or the relation with what you are doing here. It's not direct, but it's very important for biomedical application. Okay. So I'm coming from this university, which has recently changed the name. It's Université now Paris-Cité. And our lab is a biophysics and soft condensed matter lab, matière and system complex at the University Paris-Cité. Okay. Paris is a nice city, but sometimes you have some pollution peaks. And this is an example in, I think it was 2018. And so in this case, we are inhaling toxic gases, as you know, but also a lot of particles, which are coming from the activity of men. And I will be talking about this today. Okay. And to start with, I had this problem before. I cannot switch to the next slide. Ah ouais, peut-être parce que j'ai un truc. Okay, I'm sorry. Sorry?
No problem, no problem.
I do not have to run this up then. Okay, so I will make it there. So my talk will be divided in two parts. I will talk generally about inhaled nanoparticles. Okay, or do they propagate and are diffusing in the land? And in the second part, I will talk about rheology. Okay, rheology of the lung fluids and one specific lung fluid. Okay, so let's go to the inhaled nanoparticle. And when I prepared this talk and I was reading a lot of papers at the origin, I was very surprised to see what is the major origin of pollution, air pollution. Okay, so it concerns all of us because we are inhaling these particles. And the particles we are dealing with are called PM2.5. Maybe you know this term. These are particulate matter with a diameter below 2.5 micrometer. Okay, and if you look at the origin of these particles in the air that we are inhaling, the main origin are residential energy. Strange name to say. It's coming from heating and cooking in some countries, but heating and cooking, heating the houses, the buildings, and cooking. It's what the people are just cooking in their kitchen, and they are inhaling these particles. You will see the map just afterward. You have the second main contribution is agriculture. You may ask yourself, how does agriculture contribute to particles in the air? But this is true. You have natural origin, you have power generation, industry, and land traffic. We are most of the time thinking it's about land traffic and the industry which are producing the most particle in the air. This is, of course, in some close to the certain airways, not airways, autoroutes, highways, it is true, but not in this room, and not outside here in Lille, where you do not have highways close to it. So here, these are the level of this PM2.5 in Europe in 2010. It's a paper from 2010. And you recognize here the north of Italy, which is plenty of high pollution. Here's the north of Europe, or Netherlands, Belgium, a bit of Poland, and so on. If you look China, in China, you have also here a large part of particles of area, which is concerned. But what the scale is not showing, it's showing, but I'd like to emphasize here you have 35, and in China you have 100. Okay, these are from 2010. Nowadays, there are values in some big cities in the world where these values, it is expressed in microgram per cubic meter, can go to 200 to 500. Okay, so in this case, people are really breathing, inhaling these particles in large quantity. So this has an impact on the mortality, and 5 years later, a paper in Nature shows that this is a mortality related to the measurements that have been done before in 2010. Okay, and you see again, a country like India or China have the most largest contribution in terms of deaths. This is a model which is not based on measurement; it's simulation, taking into account what I showed before. In Europe, it's mainly due to agriculture, and here in the States a bit as well. And for the rest of the world, it's clean. Okay, so I came to the point here. So how do we, when we breathe, how do these particles are coming to our lungs? Okay, so lungs is the main organ that allow us to breathe. And actually, it is divided in 3 parts. You have the upper airways, which is the trachea, the larynx, and this part of the body. You have the bronchial region, and you have the alveolar region. Okay, if it's the first time that you see this picture, maybe it's so. Let me say you very simply. Here, this is this part, the upper airways. This is a series of tubes that brings the air to this alveolar region. And the alveolar region, it is where you have the exchange. Oxygen is going into the blood, and the CO2 is going from the blood into the air that we later on exhale. Okay? Conductive zone, respiratory zone. These 2 regions are absolutely important, and they are very well organized to let us breathe in atmosphere which are sometimes very polluted. So this is well understood so far. And there is a model that tells you what is a deposition profile with respect to the particles. If you have large particles or if you have small particles, they will be in your lungs differently. They will be depositing in your lungs differently. So assuming now we have particles about 2.5 microns. Okay, these particles have the probability, this is a probability function, a probability of 75% to stick in the upper airways. When you go down into the lungs, for instance, in the alveolar region, you have 20 nanometer particles. They have a probability of 50%, 55% to deposit into the lung. So what does it mean? It means here, for instance, at 2.5, it's not 100. You have 25% of particles, which are either deposited in the lower region, but it is less probable. The 25% remaining are just exhaled. So I am inhaling something, I am exhaling something, and this is 25%, 75 are sticking into the upper airways. Okay, and the same for the other one. So what you can see here, the lungs is really functioning like a filter. Here you have the large particles in the upper airways and the small particles. This peak here is shifting. So it's not completely true for the bronchial region, but it's shifting to lower particles when you are going deeper into the lungs. Okay. So this is the main message here. Nanoparticles of size below 100 nanometers, they penetrate deeper into the lungs. And everybody knows this is a major issue in our world right now, because we know that small particles, they have a lot of surface. There are a lot of available surfaces. This surface is active and can interact with biological media, which are around. Good. S'il y avait un pointer, ça serait pas mal. It's okay. So here it is a representation of the alveoli with the blood circulation. And here this is a representation of one alveoli. And what you have to see here is two things. I will not enter into too many details about the biology, but this interface, okay, is very thin. It's a very thin layer, about 1 micrometer or 2 micrometers, so very thin. And this cell, which is a little bit bulky, is secreting a liquid. And this liquid is called pulmonary surfactant. Okay, pulmonary surfactant is a liquid which is secreted in the alveoli for one good reason. One very, very good reason. And this reason is reduce surface tension between the air and the cell during breathing. If we would not have this liquid, breathing will be very difficult. And the blood, the oxygen will not go through here. Oxygen and nitrogen is coming here. Oxygen is going through this very thin interface. Okay, it is going through this thin interface by diffusion. Each time you are breathing, I am breathing, we have the oxygen that goes there by diffusing through the liquid and through the cells. It's a concept which is not obvious in the beginning, but it is important. And then, of course, people have said, what is happening? Where these very tiny nanoparticles, they are going to, say, go the same pathway as oxygen. They are going to the blood circulation here, and they are going to be distributed into our full body. This is why people have been very much concerned about the role of nanoparticles or the impact of nanoparticles in our organisms. Because these particles are small, this interface is very small, very thin, 1 micrometer, and this is possible that we have this transfer. It's called translocation, actually. How do particles interact with pulmonary surfactants? This is because then in this situation, you see that this small liquid, which is there for surface tension effect, is going to be impacted first by the particles. And so what we have investigated as a physical chemist is this interaction between particle and this liquid. Please, if you have some question, do not hesitate to interrupt me. So Fanny Musso was a PhD student, and she worked on model nanoparticle. We selected 6 types of particles. Okay, these are the names, and the sign is if they are positively charged or negatively charged. Okay, to have really a broad range of system. And we have here, as you can see, alumina, titania, silica twice, and we have also particles which are made of polymers. They are called latexes. Okay, so this is the model particles, and we want to check their interaction with pulmonary surfactant, this liquid. So the best situation would have been if we could get a human pulmonary surfactant or animal pulmonary surfactant. This is very difficult. This is very difficult to get. So we end up to using a mimetic or a biomimetic surfactant, which is called, it is this current name, Curosurf. Okay, and actually this surfactant is very interesting because it is a model surfactant as well. And this is actually a drug. This is a drug which is given, and this brings me back to my comment just before, to premature infants when they are born too early, before 32 weeks. Okay, when these small children, they are about 1 kilo, they are coming to life, they do not have this surfactant. And so you give to these children this liquid. This liquid goes through the lungs, and suddenly they can breathe normally. And before they cannot. Okay, so we got our sample from Kremlin-Bicêtre, which is an hospital, and we find a very nice doctor who collected the remaining. So he has, for instance, a 1 kilo baby, and knows that he will give to the baby maybe 2 milliliters. In his flask, he has something like 5 milliliters. So it remains 3. Once the bottle is open, you cannot use it again. So we keep them in the fridge, and every 2 months, Fanny was going to the hospital and getting the remaining of this liquid. This bottle is about 2,500 euros. And just to show you that it's quite expensive. But it saves the life of many premature babies. So if we look into the structure of these fluids, I don't know if you are used of this. I will make it simple. So we have here actually this fluid is made of lipids, phospholipids. Phospholipids. I don't know if it's clear for you. This is some small molecules which we have a lot in our body, and they have a side which is hydrophilic and a side which is hydrophobic. And these phospholipids are making membrane. All our cells in our body, they have a membrane. It's called the plasma membrane. They are made of phospholipids. Maybe you have seen some picture of this. And so what we have found is we have a lot of, but this was known, we have a lot of lipids in this dispersion, and they are making vesicles. So you have just to imagine vesicles is something like which is drawn here. Okay, you have it's empty, and you have these molecules. They are making like a soccer ball, and with a membrane. Okay, this is very famous in pharmacy, in biology. Vesicles are everywhere. Okay, so I will summarize because the first point I was mentioning is what is the interaction between these particles, which are model, with this liquid. I will not go into any details, just to see one major point, because I will use it afterwards. So this is a ranking of the interaction between particles and this Curosurf. So for particles which are negatively charged, we do not have interaction or weak. For particles like alumina, which are strongly charged positively, we have a strong interaction. This is just what you have to keep in mind. There are particles which are not interacting, very little, and particles which are strongly interacting. Interacting meaning that, we get back to what I say before. For instance, if there are the particles which are 40 nanometer, they are going to interact, they are going to stick on this membrane. This is a membrane. They are going to stick and modify the surface tension properties and the structure of the everything. particles which are not interacting, they are going to be there or there. And this we have seen. This image is a cryo-TEM image. So it's really the picture of the dispersion without any disturbance. It's a very, very fantastic technique that we have been able to perform in a special lab. And I think 2017, 3 people got the Nobel Prize for this technique. I don't remember exactly the year. Okay, so we have particles, we have Curosurf, and we are interested with rheology. Rheology, I will say a few words about it. So what is happening? Why do we have to care about this rheology? So rheology is the science which study the deformation and flow of materials. These materials can be liquid or they can be solid. Not too solid, but they can be viscoelastic, or they can be like a jelly type. Okay, this is a chemical engineering technique that is used extensively to characterize any type of liquids. And rheology measures the viscosity and also the elasticity. So why are we interested in rheology? The first reason is that the strategy I was talking about, surfactant replacement therapy that is used for the premature baby, the doctors and biologists wanted to apply it to adults. Okay, so you have a very small baby with very small lungs, and you put into his lungs via some technique, which is quite difficult. You put something like 1 milliliter of this liquid, and this liquid will go through the lungs of the baby, as I said before. So is it possible to adjust this strategy, this therapy, to adults suffering the same problem, which is called acute distress respiratory syndromes? So they just cannot breathe. Okay, ARDS. Acute distress respiratory syndrome is something that people suffering from COVID have also had. Okay, so but if you calculate here for neonates, so the premature baby, you have this dose which is given. Okay, for adults it should be 200 milliliter. Okay, 200 milliliter is more than there is in this cup. So if you give the liquid, this dispersion, to a patient which is suffering from this respiratory syndrome, you will just drown the patient. Too much liquid. So the first idea is, okay, the adult has a much bigger weight, and you have to take this into account. Is it possible to concentrate this liquid so that you reduce the volume that you will give to them? Okay. The second, and this has been done partially thanks to this Dr. Christophe Linclut from Versailles. So it is from Hospital Versailles last year. He is taking care of COVID patient, and he has tried this surfactant replacement therapy, not in this condition, of course, in much milder condition, but it has been tested on real patient and if you are interested, you can see some result of his study here on this treatment. So it was really to viral pneumonia related to COVID-19. And the second reason why we have to care about the rheology of this fluid is because there is another strategy. As I said, giving this fluid to a baby is very painful. You have to sedate the baby. It is not breathing regularly. It's really a tough because the baby is so small. And so people have invented a new technique, and this is this kind of device where now the Curosurf, instead of being put into the lungs with a laryngoscopy, it will use it will be in terms of small droplets. It will be less painful. Okay, so we need to care about this. Now I will tell you about the technique we have to measure the viscosity of a fluid which is very expensive. And this is related to micro-rheology. So you have rheology, which is for regular fluids. Micro-rheology is for small fluids. And this is the technique we used. I will not enter into too many details, but just to show you, this is the object, which is a probe that we are going to use. This is a magnetic wire. This is made of magnetic particles that you can see here. And this is what is happening when you have this object, okay, submitted to a magnetic field. Okay, we have an elongated object, which is magnetic. We submit, I am holding here the wire, and I let it go, and it goes like this. It just follows the field. Okay, it is due to the fact that you have a torque which is applied, and the torque is actually proportional to a certain number of quantity, like the volume, coupling constant, the susceptibility, and to the magnetic field. Okay, why I am showing you this equation is that because in the condition we are working, we know this, this, and this. And so we know exactly what we are applying to this object. And thanks to it, we will be able to get the viscosity of the fluid surrounding this particle. So here, this is a way to show you that these objects are magnetic. I just switch the field from there to there and back. It follows simply the fluid, the field, okay? And if I can draw your attention of this large one and this small one, you see the relaxation of the large one is much slower, okay? This is due to the friction. The wire, because it is longer, is having a friction which is much higher with respect to the surrounding. The friction coefficient is going to the length to the cube, and this is related to this. This is our microscopy room where we have this experiment. And here, for instance, we have 2 pairs of coil. So this is a real experiment. We have the sample that goes in between. This is imposing B1. This is imposing B2. They have a 90-degree phase difference. And when we apply same field on these 2 pairs of coils, we have the rotation of the wires that you can see here. So here it's about a 15 or 18 microns wire, which is rotating. Okay. This does not tell you how we measure the viscosity, and I'm going to do it just right now. Okay, it's relatively simple. Master student M1, they arrive in 2 days, they have a training and they can do measurements. It's relatively straightforward. So why is it straightforward? Associated to the experiment that we have developed, okay, we have also developed a model, and this model is this one. So imagine here, and this is a rheological model, which is called the Maxwell model. I don't know if you have heard about it. Maxwell model is the simplest viscoelastic fluid you can imagine. It has a viscosity, it has an elasticity, and it has a unique relaxation time. If you have ever read polymer books or polymer dynamics, you see that the polymers, they are described as a Maxwell model in certain conditions. Okay. Here, I am not in polymers. I am just in the fluid, which is IDEO, which is a Maxwell model. This is what is happening at low frequency. So here we are below the critical frequency. And what you see here is actually the rotation of the wire at the same frequency as the field. Okay. And you can see there is a small delay. And this delay is related to the viscosity. If the viscosity is higher, the delay will be higher. At low frequency, we have this. At high, and this is the angle that is making the wire is making over as a function of time. Okay. If now we are at a higher rotating angular velocity, we have this effect. So the wire tried to follow the field, but did not work. at some times when it is 90 degrees, just there, the torque applied to the wire is 0, and the wire goes back, and then it goes again. Okay, and you have this kind of oscillation of the angle of the wire. So it's rotating and coming back, rotating, coming back, and so on. So, okay, it's we understand it. It's not, there is a model for this. But what is very clever or very interesting here is this: the critical frequency is inversely proportional to the viscosity, and this angle, the oscillation angle, is inversely proportional to the elasticity. Okay, so you have your sample. You are going to the room, you prepare everything, you put your eyes on the microscope, you increase the frequency, you see the transition, you get the viscosity of the fluid surrounding this wire. Super simple. Okay, and the same for elasticity, you need a bit of data treatment. This is an example for calibration. In water glycerol, which is a Newtonian fluid, we have here the critical frequency as function of the reduced length, L star. This is the data for 177 wires that have been measured in this fluid. And we have the model, which fits perfectly well to the data. Okay. And these are the three or the two behaviors. The behavior where we are in the synchronous regime. Let's say we start here. We are at low frequency. It is rotating. Then we are just above the line, just there. You see it's rotating, maybe 2 turns, and goes back. It goes back, and so we are already in the synchronous regime. If your frequency is too high, you have oscillation. So by looking at this transition, synchronous asynchronous, we get the good determination of the viscosity. So during the COVID year, in 2020, Fouad Ghazemi came to the lab to make an experimental internship, and it was not possible. And he was clever enough to be able to use COMSOL and to make a little bit of fluid dynamics, and to get the velocity field around the wire. So this is a wire that rotates from the top view. Okay, and you see that the velocity, which is the highest, are very close to the tip of the wire. And in the asynchronous regime, you see that it turns and finally vanished here and goes. You see the oscillation as well. Okay, and so we have been able to. This is the side view of the wire, which is rotating like this. Okay, and you see here the velocity field. And from this velocity field, we calculate the shear rate, so the gradient of the velocity, and we could estimate a few things which allow us to make some conclusion. Okay, so the main idea here, if you have a fluid which is surrounding this wire, only a small part of the volume of this fluid will be checked, will be probed by the wire, and only for a small amount of time. Okay, it's not the whole fluid, because at the center, you see the velocity field is very close to 0. Okay, good. So another intern. I was very lucky to have such good interns these last years. Antai, she came and she looked at the Curosurf viscosity, the fluid I was talking about, the one which is given to the babies. So you recognize the vesicles. And this is what she observed. Okay, you see it's steering really a bath of a lot of these vesicles. So here it's in the synchronous regime, and here in the asynchronous one. Okay, very good. Nothing to say, it's clear. And then from this, we got the viscosity, as I explained, and this is the viscosity of this fluid as function of the concentration. Okay, so you have two characteristic concentration which are important. This is a concentration of this bottle here, 80 grams per liter. This is a concentration in our lungs, 40 grams per liter. Okay, and you see the viscosity is relatively low. It's a few times the viscosity of water. It's about here. It's 5 times the viscosity of water. It's 30 times the viscosity of water. but we get this exponential increase, or something that looks like exponential, and it is very well described in the literature. The first model is called Krieger-Dougherty, 1960 or 1959, and this is the viscosity of a dispersion as function of the concentration. There is a divergence, and we could get the divergence here as well. Okay, so the message of this slide is very simple. We have a medical dispersion, which is given to babies, which is prepared by an Italian company. But if you look at the physical properties, it's really identical to a colloidal dispersion. People having worked on colloidal dispersion of polystyrene beads, of whatever, they find this law in all type of system. Okay, so there is nothing very different here, and this is also what we expected as actually. So now, and I'm coming to the end of my talk. What is happening to these particles, to these fluids? So these are fluids that will be receiving particles when we are breathing, when we add the particles. Okay, so we have the fluids, and first we add silica. What I want first to emphasize is this is the range of investigation range we have. So this is a concentration in silica particles. And here, this is the daily nanoparticle dose that our lungs are receiving in polluted area. Okay. And here, this is 100 microgram per cubic meter. So the range of concentration we have tested is, there is an overlap with what is really occurring in some very or highly polluted area. So if we measure the viscosity, we found a very strange result. The viscosity of the fluid is decreasing. I will not enter into details because it's clearly something we do not really understand. We would have expected an increase in viscosity. This was for silica, and for alumina, which interact with very strongly with the fluid, we have also a small decrease. It has been similar results have been found on other type of colloids, for instance, in this paper. It's not completely clear, but this is not what we are interested in at this point. What happened when we increase the alumina concentration above this range, so which is a little bit high with respect to what I said before, we saw a change of behavior of the wires, and you see now the wires are just oscillating. It's a completely different oscillation, but you have an oscillation which have a different characteristic from what I explained before. Okay, and this is interpreted into the appearance of what is called a sol to gel transition, and this is a modulus, so the elastic modulus that we can measure for this new phase. So what I'm saying here, I start with a fluid, I give to the fluid a few particles which are strongly interacting, and I enter into a gel. Okay, this is in the lab, this is in our microscopy lab, this is control conditions, and so on. Okay, imagine now what is happening in our lungs if this occurs. My surfactant in my lungs now is becoming a gel, and I'm breathing, and the alveoli are just expanding, but they are expanding with the assumption that this is a liquid, a low viscosity liquid. Now we have a gel. So probably, as I say, surfactant gelification, as I've just shown, may impair the fluid's recirculation during breathing. And if you think in terms of accumulation of the dose over weeks and years, this could have a strong effect. So this is some kind, which I like to describe, of a toxicity. It is not a toxicity which is coming from chemistry, from a chemical product, but it is a toxicity which is induced by a change of physical property. Let's just see what I mean. It's a little bit like asbestos in some way. So, it was not too long. So the conclusion, okay? I did not talk about this, but also we looked at it a lot. Pulmonary surfactants, these low viscosity liquids in human or in mammals, okay, has also a protective effect toward inhaled particle because of this interaction. In some cases, we have found, but for strongly interactive particles, fluidification or jellification, which can have an effect, and for instance, that can induce a physical impairment of the alveolus environment. And we could imagine that on long term, this could have an impact on the breathing function. Okay, this is the main conclusion of my talk. And with this, I'd like to thank my co-workers, and I'd like to thank you for your attention.
So thank you, Jean-François, for the very detailed talk. And what I would say, maybe we can open the floor to discussion. So if there are some participants who would like to ask a question, just feel free to, I already see someone raising his hand. So go ahead, please feel free to unmute your mic and ask the question.
Can you hear me?
Yes.
Yes. Well, thank you very much. Very nice and clear talk. I have actually two questions. One is you put a lot of emphasis on viscosity, but my feeling is that surface tension effects should show up into the picture somehow, and especially when you have a lot of particles whose surface behavior is completely different from a surfactant. And how do you include this? That's first question. Second question is that I presume the lung has some sort of healing capability. So presumably it drains small particles out of the alveoles, so what is the process, and how is it restricted by these continuous parameters such as viscosity and surface tension? Because I have the feeling that you have a lot of Brownian motion involved there, and you probably have well, the particles moving around and sunk somewhere by some maybe specialized cells that digest these particles or trap them. And could you elaborate on that? Thank you very much.
Thank you very much for your comments. I will show you. So first, okay, the surface tension. What you say is absolutely right, and I forgot to mention it. 99% of the literature on these fluids is about surface tension and modification by the particles. Okay, so we did not, I'm not somebody working on surface tension directly. We have the experiment, but we went to rheology for some reason. But you are right, most of the studies, they are dealing with the modification of the surface tension through the addition of the particles that will interact with the first monolayer. And then when the alveoli is just increasing and decreasing when we breathe, okay, it's about 10%. We have a flow, and we have also a redistribution of the phospholipid at the interface, and particles can really impair this function. So that is for sure, and increase the difficulty for breathing. And that for sure that the second point, it's about one slide that I removed. It's about, if I have well understood your point, it's about the fact that actually there is two parts in the lungs, at least two main parts, the part which is the bronchial region and the part which is the alveolar region. But I say it's only for alveolar region. In this region, the nanoparticles, they are going to interact with the surfactant, and in the end, they will be taken up by the macrophage. This is the role of the macrophage, which then try to remove them or destroy them. Okay, but this is really deep in the lung. In the bronchial region, you have a phenomenon which is called mucociliary clearance. We were discussing with Francesco about this before, where this is not the pulmonary surfactant, this is the mucus. Mucus is a gel, and this is a very powerful phenomenon that cleans our lungs permanently. So, but in this region, as far as I know, there is no cleaning except the role of the macrophage through the macrophage. I think did I answer your question?
Yes, very well. So if I understand well, once the nanoparticles are in the alveolus, they're stuck there. We're dead.
Absolutely. But they are still a mechanism to try to prevent their effect, and these are this macrophage. Okay, but they are much less efficient as the mucus. What happened in the upper region of the lungs, this in the bronchial region, where it is very, very efficient.
Jean-François, I do have a comment about this last question. Maybe you can tell us something about it too. So actually, between the blood capillary and the alveolar wall is supposed to there must be like an interstitium where there is like lymphatic flow, which has like a clearance mechanism. Do you think that can contribute also to clear out some of the particles?
I'm not sure I understand your point. Do you think there is a clearance mechanism at this level of the alveoli?
I mean, there is some like it between the alveolar wall and the blood capillary, there is an interstitium. So there is a poroelastic layer.
Exactly. There is a membrane, which is also very thin, which is not represented. Yeah, this is true. But this is a fixed structure. It's not going to...
But there is a lymphatic flow inside, right?
This I don't know. I have no idea. It is possible. Okay. I cannot... I really do not know the answer for this question.
Okay, because that can be actually something to add to the picture, because normally the lymphatic flow in there, that's it has a clearance mechanism, so it may transport the particles before they arrive to the blood capillary. That may be, I don't know, it depends on the size of the particles.
Okay. Yeah. So it's possible. I never heard about this mechanism, but I will check.
Cool. Thank you. Okay, let's see if there is someone else who would like to ask a question. I don't see the room. I don't know, maybe I don't see the room at all. So maybe you can tell me if there is someone there who would like to ask a question, or from the audience, from the online audience.
Yeah, maybe I can ask a question.
Go ahead.
Yeah. You discussed about you tested two types of particles, the effect of two types of particles. It seems that one is able to transform the fluid to the gel. Do we know the mechanism, or do you think that it's strongly related to the type of particles or to the size of the particles only? Actually, is these two types of particles that you have tested are the common particles that we observe in pollution, or?
So, as I say, this is a very good question. As I say, they are model particles. But if you look at the literature and you see there is a report that has been written 10 years ago about the production of different particles of different metal oxide, titanium oxide, aluminum oxide, the volume which is produced in the world is huge. It's really several 10,000 of tons every year. Okay, so it is produced in places. Okay, it's and you have workers which are inhaling, this particle. So these particles, although these are model particles, they are relevant. It corresponds to existing exposure situation. The second question is the specificity of alumina. It is a platelet. Platelet, so it is really something like a platelet. Yeah, maybe 5 nanometer thick and 40 nanometer. So it's like a disc. Okay, and most probably they like to stick to the membrane. Although the other particles, the silica, they are spherical. And we never saw in TEM, I did not show you the images, but in the image we show clearly that alumina stick to the membrane. So it has really another interaction, okay? And this may explain the formation of this network of vesicles, which are now linked by these particles and produce elasticity, produce a gel phase. This is with the ends how we think it works.
You didn't say much about the, there must be a minimum concentration for this soft gel transition to happen in terms of,
Yes.
you didn't say much about it. We didn't understand.
No, there is if you put very little amount of particles, then you do not see the gel. Okay, this is for sure. If you put in the range here where you have the daily exposure dose up to 10 to the minus 2, viscosity, let's say, if you take it from far away, viscosity is not changing much. Okay, so but you can imagine that the interaction of these particles with a few vesicles may make aggregates, something where the overall viscosity does not change, but locally you may have small changes. And when we increase the concentration above this this point, then we see a change of behavior. Okay, and I show you something I have removed to make the talk shorter. But this came from a very basic experiment. I hope I will find it. This came from a very basic experiment we did. If I can find the slide. Well, a basic experiment. Where is this basic experiment? Problem second. And this you will understand. You will understand that the results are related to reality. Okay. So it was in 2015, 2016. I was working with one of the interns at that time, and we were just testing things. Okay. We put Curosurf below the microscope. We put Curosurf with these alumina particles, and we took 2 movies. Okay. After that, we saw a strange phenomenon. And then after that, I repeat the experiment myself later. I took 2 movies, and these are the 2 movies. Bon. Why is it so fast? My God. It should not be so fast. I'm sorry. Because if I want to make a demonstration, it has to be... Pourquoi ça va si vite? Movies. Ah, yes. Okay, you see the time. It's about 5 minutes. The whole. You see here the transmitted light from the microscope there is some flickering. You see some motion. Here you see nothing. Okay, you see just as it would be a photo, a picture. And when I saw that the first time, I realized something is happening. It's not normal. We don't see broad motion of the vesicles. And if you look at the fluctuation of the light that is transmitted by the microscope, you see here you have some fluctuation, and that corresponds to the Brownian motion of the vesicles, although it's a very crowded environment. And here we have the same scale, exactly same experiment, almost no fluctuation. And from this very simple observation, we saw there is something behind this. This actually what I'm showing here is a gel not moving over time. Or very tiny, very small fluctuation in the vesicle. This is the experiment that brought us to this type of experiment.
You insert particles all of the same size. You don't have a variety of sizes.
Exactly. We have our protocols. We make the mixing in such a way that it is reproducible, and we check the concentration. But we are very careful. It's because we add really a very small amount of liquid to the Curosurf, not to. I mean, it's to keep the concentration of lipids the same for all.
When you inhale, you probably inhale a variety of sizes.
Absolutely.
Does this change?
Absolutely. When we inhale, we have all types of sizes.
Does that have an effect in the way the gel is produced?
For sure. Yeah, it's for sure. And also there is something I have not said, okay, which is also crucial. And I don't know if here's the interaction, okay? It's the particles will interact with this very thin layer of liquid sunk to the surface. So there will be first an interaction at the surface, and then there is diffusion inside this fluid. Okay. In our physico-chemical experiment, we have tubes and we pour liquid like this. So it's very different. But we assume we got the same the good properties.
I was asking actually this to a colleague, actually Francesco, how do we know that what we do in the lab is the same as what happens really in the lab?
This is always a question. No, you are right. But you have it in biology. People doing experiment on mice, they know 100% that it's not representative for human, but they still continue to make. Or people doing experiment on living cells, they know it's written. But you have to do it anyway. You have to do it. So then this is how we progress.
Maybe I missed it, but you know the concentration of particles in the air, but how you relate to the concentration of particles that you would get in the surfactant tree?
Very good question.
Because
that was a
question. It should disappear with the macrophage tree, some of them.
We calculated from these curves. Okay, we assume 100, there is a model. I have a slide for this, where you will step by step, you have the model. So you have inhaled air containing 100 microgram per cubic meter, okay? And so you have this deposition profile. So you remove 50%, okay? And then you remove, again, particles because there is another factor which I forgot. There is a dispersity. These values are, and so there is a model. There is a model, and it is, you can find some, it is provided in the literature as well. But why is the concentration? And maybe I should finish with this. Why is the concentration here? When I say this is an investigation range, and this is a daily dose in polluted area. Why is this so high? Because the surfactant volume in the alveoli is very small. It's 80 picoliter. So even if you have, it's an average value for an average alveolus. If you have even a few, let's say 1,000 particles reaching, the concentration will be already high. It's because the volume is very small. And I think I did not mention this in the paper I wrote at that time. But this is really crucial.
At the start of your talk, you said that what your research is different to ours, which is true. And you said there is some kind of indirect relation. What did you have in mind?
Indirect relation?
Between our research and yours. Did you say that, or did I interest?
No, because I realized, I saw the poster and discussed with Francesco and realized, oh my God, simulation, flow dynamic simulation. So here, I don't think here it's, for you, it's not relevant pulmonary surfactant. I would say so. But what is relevant is mucus, what Francesco is doing. Yeah. Because mucus is really difficult to simulate, and it's very important. It's very important. So this is here a layer that we have in the bronchi of gel, and this gel is going up. It's going up because you have cilia that makes this liquid go up, and we swallow it. Okay. Every day we swallow about 5 to 10 milliliter of mucus. We don't see it. When I do this, and I swallow, I have swallowed maybe half a milliliter of mucus. And this is the swallowing, which belongs to the clearance. We can go in a very polluted area, and we are not going to be sick because of this mucociliary clearance. If you smoke cigarette, you will disrupt this epithelium and so on, and then it's not going to work so nicely. Lungs are much more clever than us.
Okay. So, Jean-François, is there someone else who would like to ask a question in the room? Maybe we can see if there is someone. No?
I don't think so.
I just have one last question, if it's fine for you. And that's about like the mechanism you showed before while talking about the question Christos, I think, asked you. So that's about the Brownian motion against the frozen vesicle. So basically, when there are particles in a certain concentration, so such that they kind of strongly interact with each other's, you don't observe any kind of Brownian-like motion. Is it because you're damping it, or it's because you're blocking it to propagation?
Definitely, they are a Brownian motion. Even if you have
Sure.
an assembly of colloids which are highly concentrated, okay, you do have Brownian motion, but the amplitude of the motion is very small because of the high viscosity and of the blocking of this motion with the neighbors. Okay, it's a little bit like this. Okay. Yeah, of course you have Brownian motion because temperature is not zero. So you have small movement, but you see that the particles, they reduce this motion drastically.
I meant like such a significant Brownian motion signature in the okay. So it's really like a blocking effect, you say. So it's something like a creation of particle formed barriers to damp down the amplitude of the Brownian motion in the signal. Basically, that's it, right?
Exactly.
Okay. So in this case, okay. So but then this calls for somehow a different regime when you have particles which are not forming agglomerates, but they still interact, but with somehow a sort of hydrodynamic lubrication gap in between. Because if you don't have agglomerates of particles, but still particles close to each other with a liquid in between, rather than forming barriers, they form a strong damping effect, which pass through the lubrication gap between the particles. That should be different than what you observe, right? If the concentration of the particles is a little bit smaller.
I don't know if I follow you on this one. Maybe you can discuss after the talk. I'm not sure I have understood your question, actually.
Okay. Yeah, let's postpone the discussion about this.
Okay.
Yeah, thanks a lot. So I don't see any other question from the audience. So I would say then thank you once again, Jean-François, for the very interesting and very detailed talk, and for answering so many questions. So I invite the audience to thank you again, and have a nice evening.
Thank you. Thank you very much.
Bye, everyone.